So thank you for the introduction, and I'd like to apologise to all of you for being the cause of the last-minute rearrangement of the schedule this morning, but you do have me here at last. So just to remind you where we left off at the end of Sarah's previous lecture. Oh, it's turned on. I don't know why it's not working. Does that work better? Okay, we'll try it like that. So last time, Sarah defined the bottom class, the class over Q, in the Euler system of valence and Flach elements. Which is the element for m equals 1. M is the notation we use for the index for the cyclotomic field. And this was defined as follows. So you have the embedding iota of one copy of the modular curve y1 of n diagonally inside two copies. And on this modular curve, you have the Siegel unit Cg0 1 over n. And we just look at the image of the Siegel unit under the Kummer map, giving you something in H1 of this variety. And then we just push it forward using the Italca homology push forward map, which gives us something landing in H3 of y1 of n squared. Coefficients in ZP2. So again, I remind you that here this is a Italca homology of this thing's a Q variety. So this is not a Galois representation, but it's related via the Hochschild-Serre exact spectral sequence to the Galois cohomology of the Galois representations we want to study. And today we want to extend this to get classes defined over field extensions, so on the base change of this variety to cyclotomic fields, satisfying interesting norm relations. And I want to start by recalling an idea which I think, at least in this context, was first introduced and exploited beautifully by Cato in his work on his Euler system for a single modular form. And the idea is to kind of find this constant field extension, the cyclotomic field, inside another modular curve. So you find So I'll put that in quotes because it's maybe not quite clear what it means so far, but I hope it will become clear in a moment. These pens are a bit dodgy today. So if we have U any open compact subgroup of GL2 of the finite adels, then there is an associated modular curve over Q. So this is just a specific instance of the general theory of canonical models of Shimura varieties due to Shimura and Deligne. So the complex points of this guy is one of these adelic double quotients. So here, U is your subgroup of GL2AF, and it doesn't act at all on this, and it acts on this by right multiplication, but this guy acts on both of these factors from the left. And this thing will have finitely many connected components, each of which is a quotient of H by a congruent subgroup, but it's important that it can have more than one component. And the key fact is that the fields of definition of each component are always cyclotomic fields. So again, this is part of a general reciprocity law describing Galois actions on component groups of Shimura varieties, and you always see abelian extensions of the reflex field. And I'm going to define some groups, and these are the ones that we're going to work with, and we're going to find constant field extensions inside the modular curves of these levels. This is going to be an open compact in GL2 of the finite Ls, contained in the integral finite Ls z hat. And I put congruences on the top row mod M and the bottom row mod N. And just for brevity, I'll write that as 1 mod M, M, N, N. And for A, an auxiliary integer also greater than or equal to 1, U of M brackets A, N, is going to be things that are 1 mod. I kind of split the difference between UMN and UMAN. So these definitions are lifted straight from one of the very first sections of Kato's big paper in asterisk 295. Where he defines his Euler system. And the corresponding modular curves I'll just write in this notation. So I'm always going to assume that M divides N, respectively that MA divides N. So the congruences on the top row are somehow strictly weaker than the congruences on the bottom row. Right. So these guys are varieties over Q. But there's this strange piece of structure that the base extension of Y1n to this cyclotomic field, sorry, that's a capital M, I hope that's clear, you can see as a quotient of this higher level modular curve. And I'm not going to spell out exactly what this map looks like, but in terms of adelic double quotients, it's given by the action of let me make sure I get the matrix the right way up, because I always get this wrong. It's given by the action of the matrix 1, 0, 0, M. So it's acting as Tor goes to Tor over M on the upper half plane. But the projection to this factor comes from the component group of this non-connected variety. So what we're going to do is we're going to build cohomology classes on products of modular curves with these kinds of levels, with separate norm compatibility relations in the first argument and the second argument, and then we'll put those together to get norm compatibility relations for their images down here, which is what we want. So we're going to build our elements here, prove norm compatibilities for them there, and then get what we want, which is elements on these curves, by just pushing them forward along Sm, or more accurately along the fiber product of two copies of Sm. So again, I emphasize this strategy is lifted straight from Cato's work on his Euler system for a single modular form. They're all as written, yes. Yeah. I mean, maybe I should have used different letters, because I'm going to apply this. I'm going to prove this for n and then apply it with mn in place of n. Maybe I should have called this curve y r comma s or something, and then taken s to be mn. I hope that's clear. Sorry?
Can you explain the action?
Sorry, which action?
Given by the action of 1, 0,
it's just the action of an element multiplying. Well, let me go back to the description in terms of double cosets. So on this guy, you can just take elements in here and multiply the GL2AF factor on the right by a suitable element of GL2AF, and this is the element we multiply by. So here's a lemma. So again, assume that M divides N. So U of Mn is normalized by anything that's upper triangular mod n over m. So I'm really using this assumption that m divides n. But this is really not true for if you use these things with the extra level structure, the brackets A. So the lemma says that for these subgroups it fails very badly. They're very much not normalized by this element. And in fact, the largest subgroup that is normalized by this element is the one that you get by applying part A. So this is a completely elementary matrix calculation. You can just go away and verify it, write down a bunch of congruences. But we'll see in a moment that this is what's really going to drive the machine that proves our norm relations. So keep that lemma in mind. And now I'm going to define some elements. First I'll define a map. So this is sort of a variation on the diagonal embedding. It's the diagonal embedding conjugated by the action of this element. So here, I do nothing in the first factor, but I act by this element in the second factor. And because of part A of the lemma, this gives a well-defined automorphism of the second factor of this curve. And because the determinant of this is 1, it extends to the fibre product here. It's a small detail. So here is the element I promised I'd define. This is what we call the Rankine-Eisenstein class. And it's the push forward by the map I've just defined of the Siegel unit on this curve. So notice that the Siegel unit doesn't know what n is. It depends only on n. So we're somehow going to get norm compatibility in n from the properties of the Siegel units, and norm compatibility in m from the properties of this embedding iota and how it gets moved around by the action of certain quotient maps on these varieties.
What is n brackets L?
Let me just rewind a moment. It's the second flavour of Cato's higher level modular curve. So you put the congruence on the corner element, but not on this this top diagonal element.
What is the notation 1, 1, 0, 1?
Well, it's for an element of a product of groups. You're acting on the first factor trivially, on the second factor by this 2x2 matrix. Essentially, it would be enough there to take pretty much any unipotent element of GL2 times GL2 that isn't in the image of the diagonal GL2. And we had this map SM from these funny higher level modular curves down to the ones we want to study, which are just the base extensions of y1 of n. And this is in H3 et al. Of the y1 of n squared with scalars extended to q mu m coefficients in ZP2. So these are going to be our Euler system classes. And we want to prove norm relations for these things, and what we're going to do is prove them for these guys and then kind of push the information through SM. So now I'm going to explain the easiest case of these norm relations, which is when you want to vary m, but varying it through powers of p. But first I'm going to note that there's an easy norm relation. If you take this Rankine-Eisenstein guy, and you just push it forward along the natural quotient map. Sorry, my notation's got a bit screwed. So here L is some prime. So this map is it's a finite covering map of algebraic varieties. So it induces push forward maps on Étale cohomology, and although Étale cohomology may sound scary to work with, it's actually really rather straightforward to prove that this just sends this guy to the corresponding guy on this variety. As long as L divides N. And there's some simple Euler factor modifying this if L doesn't divide N. So this is a direct consequence of norm compatibility properties of the Siegel units.
Which I didn't state.
So there's an analogous statement saying that if you delete the squares and you just look at the class in H1 coming from the Siegel unit here and the corresponding Siegel unit here, then these are compatible, and this you just prove by hand from the infinite product expansions that Sarah wrote down, and then it's easy to check that that's compatible with the push forward maps into the product of modular curves. So this is easy, but it's not. It only gives us half of what we want. Because in order to see what happens when you change m over here, you need to add an extra power of L here and here, and it's changing m that's the difficult bit. And if you try and do the analogous thing here, if you take the natural quotient map from this variety to this variety, sure, this exists, but if you push forward this guy, you get a completely unwanted factor of L squared. Which is actually because this guy is the pullback of up to a simple transformation is the pullback of this guy. So when you norm it back down again, you multiply by the degree. So this is not what you want. These, if you take L to be p and then m to be a large power of p, you just get denominators piling up on you as you go up the tower. So this is very bad. So what we do instead is we take a funny twisted quotient map, a twisted degeneracy map, which I'm going to call Tor-L. I'll define it on one copy, but obviously you can take two copies of it. And it's given by the action of 1, 0, 0, L. It's a bit like somehow one step of the map SM I described before. And that allows me to state the main theorem I want to prove today. Well, m divides n. I was going to write L divides m and L divides n, but m divides n anyway. So let me write that. So I push forward the Rankine-Eisenstein class by this twisted degeneracy map. And what I get is a Hecker operator instead of this power of L squared. So this is the transpose of the usual Hecker operator UL. This came up in Romyar's lectures as well, that he was using a transposed Hecker action, which is convenient because later we're going to invoke Poincare duality, which exchanges this with the normal UL. And this just means that I have a Hecker action in both factors of my modular curve, and I act in both at once. And before I give you the proof, I'll just tell you what the corollary is. So the Galois co-restriction map is a special case of these étale cohomology push forwards. And you get the statement formally analogous to this one. And deducing the corollary from the theorem is virtually trivial. You just need to check that the UL interacts with the SM that we use to define the Venn and Flach element. But the key thing is to prove the theorem about the Rankine-Eisenstein element.
You meant that the tau L interacts with the SM?
No, well, I mean that if you... I actually meant what I said.
Okay.
There is a diagram connecting tau L, SM and SMN, out of which the Galois co-restriction naturally drops out. So, even though I've only just started on this page, I'm going to start a new page because there's a rather large and quite important diagram that I want to do a decent job of drawing. So in this diagram, any unlabeled vertical arrows will just be the natural quotient maps between these things. I mean, this is a double quotient of some modelic space. This is a double quotient of the same space by a slightly larger group, so there's a natural quotient map. This map here is iota MLN. This is the same thing for M rather than ML. So both of these maps are closed embeddings. They're just the diagonal embeddings. And there's a map here. And notice that I've got brackets L here, but I've not got brackets L here. I'll call that over to M brackets Ln. And this again is the natural quotient map, but this one is twisted by the action of 1, 0, 0, L. So the effect is that this thing down here is tau L. Or rather, the product of two copies of tau L. So the fact that you can draw such a diagram and that it commutes is virtually obvious. But there are two important properties of this diagram that I want to emphasize. The first one is that this middle arrow, let me do this in a different colour. I always used to hate it as a student when lecturers would draw a big diagram and then they would gradually go in and annotate it and change bits of the diagram and it was impossible to take notes. But I'm going to commit that sin myself, but I'll do it in red to mark that it's sinful. So the important thing is that this map is injective. It's a closed embedding of varieties, even though this looks like it somehow has a bigger level than this guy over here. The important thing is that all of these arrows involve conjugation by 1,1101, the element I was asked about earlier, and because that doesn't normalize this level group, and in fact the largest level group that it does normalize inside that is this one, it turns out that this arrow is injective. So this is why I had part B of my lemma earlier.
That is an L, right, in that matrix?
Sorry?
Very small matrix of the arrows, an L, right?
Yes, that's an L. And it's that on actually on both factors of the curve. Both curve factors of the surface, I should say. So that's the first key property, and the second one concerns this square here, which for consistency with the notes I'll mark with a diamond. So this is a Cartesian square. It identifies this guy with the fibre product of these guys over this. So once you know that the horizontal arrows are closed embeddings, both of them, in order to check that it's Cartesian, all you need to do is to calculate the degrees of the vertical maps. And it turns out they do, but they have the same degrees, but in a different way somehow. Here, we've added a congruence mod L going from this curve to this curve, but we've done it twice. So we've got somehow two factors of L in the top corners of both matrices. So this is degree L squared. Whereas here, we've added two congruences mod L on different entries of the same matrix, but it still gives you L squared. I should maybe have done that in red as well. So Cartesian diagrams are very good for these kinds of norm relations, because there's a lemma about Cartesian diagrams which is called the push-pull lemma. And it allows you to reduce calculations about push forward along a complicated map to push forward along another much simpler map. So let me just draw the diagram of this lemma. So here x, y, z and w are pretty much arbitrary smooth varieties. So if I have a diagram like that and it's Cartesian, I have two ways of getting from the cohomology of this guy to the cohomology of this guy. I can either push forward and pull back, or I can pull back and push forward. And the composites you get, let me make sure I write them right way around. They both agree. So if you have a cohomology class down here, the two ways of getting it to the top corner, they agree. So obviously I'm going to apply this to this square down here. So I'm going to apply it to diamond and to the cohomology class down here. And to the Ziegel units class up here, down here. So I'm going to use the fact that the Rankine-Eisenstein class here is defined as the push forward of this cohomology class here. So one of the two things that I get by doing my push and then pull, push forward to here, you get the Rankine-Eisenstein class, and then you pull it back up to here. So the pullback of the Rankine-Eisenstein class from here to here is equal to something else. What's that something else? It's the push forward of the pullback of the Ziegel unit here. But in my construction, I only ever use Ziegel units that depend on n. So the input for all of these things is G0, 1 over n, and they're compatible under pullback. So let me make sure that this diagram is still visible as I'm talking through it. So the two things that I agree from this lemma are this push and then pull, which is just the pullback of Rankine-Eisenstein Mn. And on the other hand, this pullback and then push. But because this thing is equal to this thing, and push forwards are functorial, that's the same thing as the image of the guy here under push, push. And that's just the push forward of the Rankine-Eisenstein class up here. Sorry, I'm leaving out my C's by mistake. So we have a guy down here and a guy up here, and what the push-pull lemma is giving us is the pullback of this one is equal to the push-forward of this one. And the place they meet, they're equal. And now we just push forward both of them along the only map in the diagram we haven't used yet, which is this one. So then we get to the equality of the images of those two things down here. One of those things is the thing we're trying to study. Sorry, that's an ML. And it gets to be equal to the image of the Rankine-Eisenstein class down here under this pullback composed with this push forward. But this little roof is exactly the Hecker correspondence UL, or rather its prime version. So that's precisely what we were trying to prove. Because this little process here is the definition of this Hecker operator. So that completes the proof of this norm compatibility relation in this easiest case where you've stripped away all of the Euler factors by assuming that L divides every other part of the level. So I just want to pause for a moment and say that this kind of diagram seems to be quite a general and powerful tool for proving norm compatibility relations for cohomology classes attached to modular varieties and general Shimura varieties. So you'll see another instance of that in Sarah's lecture tomorrow, where she'll be building a precisely analogous diagram, but where all of the varieties along this side are Ziegel modular threefolds, so Shimura varieties for GSP4. And in work of ourselves and some of our students and postdocs, several more examples of diagrams like this have emerged as the key steps in proofs of norm compatibility properties for quite a number of new Euler system constructions. So there seems to be a lot of mileage in diagrams of this type, and one of the project groups is currently having fun trying to build another example of this kind of diagram. So now, having talked at great length about how much I love this diagram, I'm going to hide it. It will return. So that was the proof of the basic norm compatibility relation at the level of absolute Étale cohomology. Étale cohomology for varieties over number fields. But we want some statement about Galois cohomology classes for some particular pair of modular forms. So let me just project to the quotients corresponding to some eigenforms. So I take f and g eigenforms of some level n. So if I start with two eigenforms of potentially different levels, I just choose some new level divisible by both of them and promote them up to that level by taking appropriate L stabilizations. So I definitely don't want to assume that they're new. And I'm going to assume that P divides N. Again, I can arrange this if I want by P stabilizing everything. And there's a key assumption I want to make at this point, which is that these guys are both ordinary. So if you recall how the Galois representations were defined, they were defined as quotients of the Étale cohomology of modular curves. So I'm going to be a little bit more specific about how I define those things. I'm actually going to construct the dual representation sorry, I should have tensed it up to some coefficient field big enough to contain the coefficients of f and g. So I just arranged that the Hecker operators in the first factor act as they do on f, and the Hecker operators in the second factor act as they do on g for every prime L.
You assume that weight?
Yes. Thanks very much. These are weight 2 eigenforms. Everything I've explained can be done for general eigenforms of weights greater than or equal to 2 by working with Étale cohomology with coefficients, but that's not something I want to get into. So thank you for the reminder. These things are all taken to be weight 2. So here I'm using the transpose Hecker operators, the TL primes. And you interpret this as this is the same thing as UL primed when L divides the level. So as a Galois representation, this thing is actually a direct summand, but it's not a direct summand as a Galois times Hecker module. I've exhibited it as a quotient, as a Hecker module. And that means that H1 Étale of let me do this over a general cyclotomic field Sorry, that wasn't Étale cohomology, that was Galois cohomology. But this is Étale cohomology. And because of the particular way I've arranged these things using Hecker operators, the action on this guy of the Hecker operator up primed corresponds to multiplication by APF APG. So that's important because this factor is a unit because of my ordinarity assumption. Let's go. So we can define this cohomology class, renormalizing by powers of APF, APG, and these things are now co-restriction compatible in R, as long as R greater than or equal to 1. So you can regard these as a class in the inverse limit of cohomology of these V's, but without the denominators growing as you go up the tower. So this, in other words, is a class in the Iwasawa cohomology tensored up with lambda, to use the formalism from Chris's lecture earlier, in terms of this thing he was calling bold T. So we've constructed the p direction of an Euler system, a collection of canonical global cohomology classes up the p cyclotomic tower, satisfying norm compatibility relations. I haven't told you how to prove norm compatibility relations when M is not a power of P. The awkward case is when you introduce new primes into the level which do not divide the level. Sorry, new primes into M that do not divide the level. That's better. They're more difficult, and the answer is more complicated because it involves a degree 4 polynomial in the Frobenius, which is the Euler factor. But it does come out, and you can show that these classes, as I've defined them, satisfy a norm compatibility involving something that's at least close enough to the correct Euler factor to get the machine of bounding Selmer groups to work. So this is the construction of the valence and Flach element Euler system. And that's all for today, and Sarah will take up from there tomorrow, explaining how to extend these ideas to construct an Euler system for GSP4. Thank you.
Any questions? confusion of three new forms?
Sorry?
Can something be done for the confusion of three new forms?
Three forms. Yes, so that's a more difficult problem. One should distinguish between whether you want to look at all twists, whether you want a full Euler system attached to the product of three modular forms, or one of these anti-cyclotomic self-dual Euler systems in the style of Colli-Vargin's Higner points. The problem is there isn't a simple formula for the L function attached to a product of three modular forms in terms of Eisenstein series on a product of three modular curves or something like that. You can get the central value using formulae due to various people, including Eugenio, but to get all three forms, you would need to go up to some Siegel modular variety for GSB6 or something like that. And I don't know of anyone of any work that's succeeded in working that out. So one modular form or two modular forms seem to be as far as you can simply get so at the moment.
Other questions?
I'm just asking because I might be missing something. So you said the denominators are bounded as R goes to infinity, but then you said P does not divide these, so there's no denominator at...
Perhaps I didn't explain correctly what was going on. The norm relation that I have explained is about the case when M is a power of P. And this is a separate sentence concerning some other construction. But are you referring to the fact that this is a unit and thus the denominators are actually trivial?
Yes.
Right. That's whether the denominator is trivial or not depends on whether you choose on which lattice you choose. There are multiple possible ZP lattices inside the F tensor Vg. If you work with the lattice that comes from the image of the cohomology of y1 of n squared with ZP coefficients, then yes, the denominators with respect to that lattice are not just bounded, they're zero. There's no denominator. But that is in a sense not the most natural lattice to work with, particularly if you're in a situation where the mod P representation is not irreducible. And then perhaps you might want to work with the lattice coming from the closed modular curve, for instance. And then you might have some finite denominator, but the point is that it won't grow in the cyclotomic tower.
Okay, maybe we'll postpone further questions for the break, and thank David again.